Alright, for the second half of Chapter 7, this is Worksheet B. And so we're going to be looking at numbers 2 and 3 on this video. So starting off here with number 2. So given a curve, given a function up at the top, says find the values for where the derivative equals 0. So a couple things you could do with this. You could distribute that in and then do the derivative, which is probably the easiest. Or we could use the product rule. Whatever's easiest for you at this point. So I think the easiest path would just be to distribute. So for this one, I'm going to get 2x to the third minus x to the fourth. And that's pretty easy from there to take a derivative. So in this case, we'd be looking at 6x squared minus 4x to the third. And this one is asking to find the values for x where the derivative equals 0, so we're going to set that equal to 0. Best way to solve from here would be to factor out a greatest common factor. So in this case, 2x to the second could come out of each term. So that's going to leave you with 3 minus 2x. And anytime you solve by factoring, it just means you set each factor equal to 0. And then solve from there. If I set this equal to 0, I'm just simply going to get 0 for that solution. If I set that equal to 0 and subtract the 3 and divide by negative 2, I'm going to get 3 over 2 for x. And so that was part A, just finding the values for x where the derivative equals 0. So moving on to part B. So take those answers. So find the maximum value of y, and then we're going to use a first derivative test to prove that it's a maximum. So to find a member, a max or a min or any stationary point, that's always when you set the derivative equal to 0. So these guys right here must be stationary points. We just don't know their classification. We don't know if it's a max or a min or a point of inflection. And so this one is asking us to find a max value of y. So in this case, I know these are my two stationary points. If I were to plug a 0 into the original function for x, I would just get 0 as a result. So I know one of the stationary points is 0, 0. On the other guy, if I were to plug in 3/2 in for x into the original function, we're going to see something like this. So there we are plugging in 3/2 in for x. And so that's the result that I got. Let me go to math, fraction. So we could see it as 27 over 16 as a fraction. So either decimal or fraction on that. So I'll just keep it as 27 over 16. So in this case, obviously, this is bigger than this, so this must be my maximum value of y, which these could have been done on a calculator. If we were to graph the original function, just look at the curve, you can identify where that maximum value is. Whenever you graph, under calc, you can always use these items to find a minimum or a maximum on a curve. And so those can be done on a calculator, but we always want to make sure we know how to show the work for this if asked. So show that it's a maximum with the first derivative test. That just means we want to test the numbers surrounding this guy. So I'll kind of use a little number line to show the work for it here. So if this is 1.5, which is the one that we're testing right here, I know at that point I have a slope of 0 at that point. Because of the work that we've done so far based on this. So we know the slope is 0 on there, so let's test a couple numbers on either side. So if I wanted to test a number smaller than 1.5, such as 1.4, and then we'll test one on just the other side of it at 1.6. You always want to test some numbers that are close to the number that you have. So if we were to plug in 1.4 into the derivative, we're going to see what kind of sign do we get out of that. If I plug 1.6 into the first derivative, and we're going to see what kind of signs we're getting out of that. So we're going to take a minute here to plug those in. So when you plug in 1.4 into the derivative, so we're plugging into this function right here, you'll notice any number to the left of 1.5 that's greater than 0, because remember that's when I hit my next turning point. But less than 1.5 and greater than 0, any number you choose, such as 1.4, is going to yield a positive number, which means all the slopes in that area are positive. So the numerical value itself is kind of irrelevant. We just wanted to know whether it was positive or negative. So numbers on this side of 1.5 came out with positive slopes. Remember, this was a zero slope. If we were to plug 1.6 into the derivative, or any number greater than 1.5, you're going to find out that it comes out to be a negative number. And so because of that, that means the slopes in this area are negative. So if you just sort of think about this logically for a minute, I have a positive slope here. So it's positive, which means my curve is going up. And then all of a sudden I hit a zero slope at 1.5. So I'm hitting that max right there of a zero slope at 1.5. And then my slopes turn into negatives on the other side of that, which means my curve is doing something like that in that area, because it was going up right here. All of a sudden I hit a zero slope, and then it starts going back down on the other side. So that's how we prove that it's a maximum. Anytime your signs change from positive to negative would only occur at a maximum point. And so that's how the first derivative test works. So that's how we show that it's a maximum. So calculate the gradient of tangent t to the curve at this point. So pretty classic just derivative problem on this one. So just looking for a gradient, which means derivative. So I want to plug in an x value always into my derivative to get a gradient. So if we take the derivative that we found earlier, which was 6x squared minus 4x to the third, so by plugging a 1 into the derivative, we can come out with the gradient at that point. So if I plug in a 1, it's just going to be 6 minus 4, which is 2. So that's our gradient where x is 1. So use this result to now find the equation of t. And remember, finding the equation just means point slope. You have your point, you have your slope. So we're just going to plug that into our point slope formula. Again, the formula packet calls it the gradient formula, which looks something like this, the way we've always done it in the past. In earlier math courses, it takes the denominator and multiplies it over to the right, which kind of saves you a step anyway, so I usually just start there at that stage. But a little cleanup on that, so we'll distribute the x. So it's going to become 2x minus 2, but when I add this one over, that minus 2 is going to jump up to minus 1. So there's the equation of that tangent line. And as always, formatting, just follow the directions. And if it doesn't say, then any format would be acceptable. So if you want to go slope-intercept, if you want to put everything onto the left side in kind of a standard form look, you could do that as well. So going on to part E, verify that the line tangent to C at 1, 1, which is what we've already done, meets line C again at -1, -3. And so we just want to show that there's a common point there. So just doing a little number testing, we're just verifying that this point is on line C. So all we have to do is really just test the numbers and make sure they fit. So if I plugged a -3 in for y and a -1 for x, we're just testing to see and make sure that those do fit the equation. Meaning when I plug in a -1 for x, do I get -3 as my answer? And so in this case, we are verifying that that fits. And so it did come out to fit that point. So we know where we're showing. Again, you got to show the work on that stuff when it gives you directions like this. So really important that you make that nice and clear that you showed the work. So last part on this, part F, just sketch the graph of the curve together with its tangent line. So obviously if you had this were a calculator scenario, this would be real easy to verify on our calculator and make sure this comes out right. But otherwise, if it was a non-calculator scenario, as half of the IB test is non-calculator, then we just want to use the information that we already have. So anytime you make a sketch of a graph, you must always label your axis values and label your scales on your axis. So really important that you do that. It can't just be a total random sketch without any numbers, or you wouldn't get credit for it. But in this case right here, so we had our curve from up above. We had a couple turning points. We had one we found at 0, 0. We discovered that we had the maximum at the coordinates 3/2 or 1.5. So let me throw in a few numbers here. So at 1.5, and then went up to 27 over 16, which was like 1.7-ish. So we'll put in a couple numbers up here. So somewhere about this neighborhood, we knew we had a maximum at those points. So those were our two turning points, and again, we knew this was a maximum, and so we knew we had the graph doing something like this. On the other side of 0, 0, if we wanted to verify for sure, like if this were a non-calculator test, then again we could just test some numbers on the other side of 0 to see whether this is has negative gradients, so it's doing something like this, or if it has positive gradients and maybe this was just a point of inflection. And so we could do it again, a sign test on the other side to see what the gradient was doing on that side. The other thing you could do is just pick a number and plug it in. For example, if I just plug in a -1 into this function, I can get another point on my graph. So if I did plug in a -1 for this, so 3 times -1 would be -3, which means I have the point -1, -3. So there's another point on my graph, which means we did have that point of inflection going on there. So that means our curve was doing something like this, where it came up and then it leveled out right here and became flat just at the point of 0, 0, and then went back up, hit that maximum right there, and then started coming back down. So you can kind of see the signs on that would show that it was a positive to a positive to a negative. So all right, that's how we knew that was a max. That's our point of inflection, because the signs didn't change on either side of it, even though it did have a 0 gradient at that point. So there's kind of the sketch of the curve. But just to show that tangent line T on that graph, we could just use the couple points that we were working with up above. So we knew we had the point at 1, 1. So there was a point right here. We had also -1, -3, which is the other one that we've already come out with right there. And so there's our tangent line, if I can draw that accurately as best I can. So there we go. So there's a good sketch of the graph. We got some scale numbers labeled to make sure that we were not doing just a random sketch, and those things were accurately placed on the grid. All right, moving on. Number 3. So for number 3, we got this airport that's 3 kilometers long. So airplane touches down on a runway at point T and immediately begins to slow down. So point A is at the western end and B is at the eastern end, and point P is a marker somewhere, anywhere we can put on the runway. So so as it slows down, distance function that they're calling S from A is given by this. So we have a displacement or a distance function right there. T is in seconds after touchdown, and then C meters is the distance of T from A. So yeah, so starting off with part A, so the airplane touches down at 900 meters, and so they're just kind of helping us verify right there that that's 900 meters from point A. And so again, that's the distance of T from A. So they're giving us like a 900 meter length right there. So find the distance traveled in the first 5 seconds after touchdown. And so this one's asking for distance, so we can plug our 5 into the distance function to get that answer. So we just plug in the numbers into that original function up there. We had the 900 already in there for C. And so if you do a little cleanup on that, you come out with 625 for that distance. And so that was just plugging in a few numbers that were already given to us. So again, the 900 went in there for C, and they made that pretty clear right here. 5 went in for T. Second part, write down an expression for the velocity, which we know is the derivative of our position function at T seconds after touchdown. So we know we're going to need a derivative for part 2 here. Get a new sheet of paper real quick. So we need a derivative of the original, and again, our constant would go away. So if we just do our derivative, so velocity is the derivative of the position function. So 150 minus 10t to the first is going to be our derivative function. And this one just said write the expression for time t, which is what we just did. So now that we have that, we can now find the airplane's velocity after 7 seconds, which means you just plug in a 7 into your derivative. Now that we have the velocity function right here, just plug in the 7. So 150 minus 70 is going to get you 80. Is the velocity, 80 meters per second at 7 seconds. So airplane passes the marker at P with a velocity of 70. So now they're giving us the velocity. So they want us to find how many seconds after it passes the marker. So we can now just say that the velocity equals 70, and we're just solving for t. So taking our velocity function, setting it equal to 70, and now we can solve for time. So subtract the 150, you got negative 80 divided by negative 10, and you're going to get 8 seconds for that guy. So for the distance from P to A, so now they're kind of directing us back to the distance function or the position function that we had from up above. And we now know the time from P to A was 8 seconds. So that's what was like defined for us right here is after it passes point P. So we had the velocity at that point, and so now the distance from P to A is coming from the original function that we had right here. If we just plug in the 8, then we can solve for the distance on that. And so we already had the 900 in there. Just plug in the 8. And you're coming out with the distance for that part. So last step here, so show that if the airplane touches down before reaching point P, that it can stop, meaning it would have a 0 velocity before reaching the end. So for this guy here, we first need to solve for some time on this one. So remember, this one is talking about a velocity of 0 because of that wording right there. So if we take our velocity function that we had earlier and set it equal to 0 because it's coming to a stop. So if you subtract your 150 and divide by negative 10, that tells you that it's going to take 15 seconds to create a 0 velocity, meaning it takes 15 seconds to stop. And so if we look at our distance function for that, our position function, after 15 seconds, how far has it traveled? So if we take our 15 seconds and we plug it back into the original function here, you're going to come out with, it looks like 2905 for that guy. And so that means it took 15 seconds to travel 2,905 meters in this case. So when t was 15, or at 15 seconds, the distance or position came out to be 2905. And so we're showing that it did have enough time to stop because based on this statement right up above in the very first sentence, it told us that this was 3,000 meters long. So if the runway was 3,000 meters and 15 seconds, it would travel this distance, we're showing, yeah, that's less than 3,000, so it did stop before it hit the end of the runway in that case. Something that would be a little worthwhile to look at real quick, just as sort of an additional question here, is what would be like the greatest value for C in order to ensure that this thing would stop in time before it reaches point B. So like in this case, if we know that it takes 15 seconds to stop, and we know the entire distance of the runway was 3,000, so we know if the total distance is 3,000, what would C have to be in order to make sure that it stops before the end of the runway? So that's our total distance. We know that it takes 15 seconds to stop, minus 515 squared. So here's sort of a spin-off question that you could certainly run into, is we can now, knowing that it takes 15 seconds to stop and that's the total distance, we can now find a value for C for what that would need to be in order to make sure, according to this statement that we're seeing down here, in order to make sure that it hits a certain point on the runway with enough time to stop before getting to B. So that's another spin-off of this question that we want to know how to do.